This is The Synthetic Lens. I'm David Carver. The viral version of this story is simple. AI is running out of power. That line is useful. It is also too sloppy to leave alone. The world is not running out of electricity because people are asking chatbots to write emails. Data centers are still a limited share of global power demand. But look at what the market just did. On June 30th, Bloom Energy and Brookfield expanded an AI infrastructure power financing framework from $5 billion to $25 billion. The pitch is not just buy electricity. It is power, compute, data center infrastructure, and capital bundled together from the start. That is the why now. The AI boom is moving from model demos to physical constraints. The next bottleneck may not be the benchmark. It may be the substation. Marcus Chen is here. Marcus, start with the numbers, but translate them for audio. What is actually happening?
The clean version is this. AI is not exhausting global electricity. It is running into local power systems. The International Energy Agency estimates that data centers used about 415 terawatt-hours in 2024, around 1.5% of global electricity consumption.
In its base case, that more than doubles by 2030 to about 945 terawatt-hours. The IEA compares that number to roughly Japan's current annual electricity consumption. So this is not a rounding error, even if it is not the whole global grid. And the IEA adds another useful scale check. A typical AI-focused data center can use as much electricity as 100,000 households. The largest campuses being built can use 20 times that.
So the honest version is not that AI is out of power. It is that AI is becoming a power planning problem.
Exactly. Data centers concentrate enormous loads in particular places. They need reliable electricity, substations, transformers, transmission, cooling, backup systems, land, permits, and interconnection agreements. A model company can announce a frontier system in a blog post. A utility cannot announce a new transmission corridor into existence.
That mismatches the constraint?
IEA says a data center can be operational in 2 to 3 years, but energy infrastructure often has longer planning and build times. It also notes that grid components like transformers and cables have seen wait times double in recent years.
So the problem is not just how many kilowatt hours the sector uses globally. It is whether a specific region can absorb a specific load at a specific time without raising reliability risks or pushing costs onto everyone else.
Bring this down to the United States.
Lawrence Berkeley National Laboratory's 2025 update estimates that U.S. data centers could account for 11.8% of total U.S. electricity use by 2030, with a scenario range from 9.5 to 15.3%. Their reference case puts U.S. data center electricity consumption at 649 terawatt-hours in 2030. The uncertainty range is wide, 521 to 843 terawatt-hours.
Those numbers are not small. But the key is that they are not evenly distributed. Northern Virginia, parts of the Mid-Atlantic, Texas, Georgia, the Northwest, and a few other clusters matter because that is where the load arrives. And national percentage hides the local fight.
Goldman Sachs Research made a sharper near-term claim.
Yes, Goldman projects U.S. data center power demand rising from 31 gigawatts in 2025 to 41 gigawatts in 2026 to 66 gigawatts in 2027.
That is a huge jump over 2 years. But Goldman also says schedules erode with time. Roughly 60% of capacity scheduled for the next year is expected to materialize on time, dropping to roughly 50% within the next 2 years. Delays and cancellations are not a footnote. They are part of the forecast.
So benchmark progress and deployment progress can split.
Exactly. A lab can improve a model while the data center build-out slips. That means capability exists in theory before it exists in available capacity. The model race becomes a cue for power, cooling, equipment, and local permission. Ingrid Halverson joins us. Ingrid, if electricity is becoming a bottleneck, what is the market doing?
It is bundling the bottleneck into the product. The Bloom and Brookfield deal is the cleanest signal. The language matters. They describe a model for AI factories that integrates power, compute, data center infrastructure, and capital from the outset. In other words, the pitch is no longer build a data center, then buy electricity. The pitch is package the electrons, the servers, the building, and the money together so the customer can get capacity faster.
That sounds efficient.
It can be. It can also be a sign that ordinary infrastructure channels are not enough. If power were easy, you would not see this much effort to bring generation, financing, and compute under one deal structure. On-site fuel cells, gas, nuclear agreements, geothermal, storage, and retired coal site reuse are all symptoms of the same problem. Data centers want firm power on timelines the traditional grid was not built to satisfy. The business question is, who pays for the workaround? If a hyperscaler funds its own on-site power, that's one model. If grid upgrades flow through regional rate bases, ordinary customers may end up subsidizing infrastructure that primarily benefits private compute demand.
That is where this stops being a pure tech story.
Right. Once data centers become large enough to affect capacity markets, rate structures, and reliability planning, the story becomes a question of allocation. Who gets cheap power? Who gets reliable power? Who gets jobs? Who absorbs the noise, the water stress, and the cost of upgrades?
Elena Vazquez is here. Elena, we now have companies talking about AI factories, fuel cells, and nuclear-powered data centers. How much of that is real, and how much is stagecraft?
Both. The real part is that power has become strategic. The Department of Energy's own framing includes on-site generation and storage, retired coal facilities, rate structures, geothermal, advanced nuclear, long-duration storage, and efficient semiconductors. That is a serious policy menu. And the nuclear piece is not floating in isolation. Valar Atomics is part of the same DOE reactor pilot atmosphere that has been pushing advanced reactors toward criticality by July 4th. So when a nuclear data center demo appears, it plugs into a real policy lane. The stagecraft part is that every energy solution wants to be photographed next to AI now. The Valar Atomics NVIDIA story is a good example. Reports describe a Utah demonstration around nuclear power and AI data center infrastructure. That is visually irresistible. Reactor, Blackwell chips, near waterless cooling, the future arriving in the desert. But the scale matters. This is a demonstration, not proof that nuclear-powered AI campuses are commercially solved. The useful image is not the grid problem is over. It is closer to a first trickle of power being made legible by AI branding.
So why mention it?
Because demos reveal where the pressure is going. The fact that a nuclear data center demonstration gets attention at the same time a $25 billion on-site power financing framework is in the news tells you what the market is nervous about. Nobody wants to be the AI company with the smartest model and no place to plug it in. There is another technical wrinkle. More efficient chips and models do not automatically reduce total power demand.
Because efficiency can lower the cost of using more compute.
Exactly. If inference gets cheaper, demand can expand. If agents become useful inside software development, customer service, research, finance, logistics, and entertainment, the question is not just how efficient each token is. It is how many more tokens the economy decides to run. IEA includes a high-efficiency case where better hardware, software, and infrastructure lower demand versus the base case. That matters. Efficiency is not fake, but the base case still has data center electricity demand doubling by 2030. The gains have to outrun adoption.
And adoption is not just consumer chat. It is enterprise workflows, AI coding agents, video generation, synthetic data, robotics, security analysis, and model training. Every new AI can now do this headline is also a load forecast somewhere.
Let's put the counterargument on the table. Data centers are not the largest source of global electricity demand growth.
IEA says they account for around 1/10 of global electricity demand growth to 2030, less than industrial motors, air conditioning, or electric vehicles. So why should this be a TSL episode?
Because data centers are a small global share with an unusually concentrated local footprint and unusually strategic customers. A household air conditioner does not arrive as a single 100-megawatt interconnection request. A hyperscale campus can. A steel mill is also power-intensive, but it does not usually carry the same geopolitical story about model supremacy, cloud lock-in, and national AI capacity. This is why the distribution matters more than the percentage.
And the politics are already local. Communities are not voting on global electricity demand. They are fighting specific projects near homes, farms, water systems, and transmission lines. That is where the legitimacy question lives.
If a data center promises jobs and tax base but asks for enormous power and water commitments, residents will ask whether they are hosting infrastructure for their own benefit or for a distant cloud market.
The technical answer may be better siting, more flexible operation, on-site generation, and smarter interconnection rules. The political answer has to include transparency. People need to know the scale, the energy source, the water plan, the rate impact, and who is responsible if the project changes.
That connects to a bigger AI governance point. We often talk about access as if it only means model weights, APIs, safety filters, or export controls. But power access is becoming part of AI access. If only a handful of companies can finance generation, reserve grid capacity, and wait out interconnection queues, then the frontier narrows before the user ever sees a model menu.
That is the quiet market concentration risk. Compute was already expensive. Power makes it more vertical. The winners are not just the teams with the best researchers. They're the firms that can sign energy deals, influence siting policy, secure chips, finance campuses, and absorb delays.
And that changes how we should read model announcements. A new model is not just a capability claim. It is a capacity claim. Can the company serve it widely? Can it price it sustainably? Can it run the agents people want without token budgets or power budgets breaking the business model? That is why Meta's internal token spending stories belong near this conversation, with a caveat. They are not about grid electricity directly. They are about the same operating cost collision showing up inside the product. Power is the physical limit. Tokens are the product-level meter. Both are ways the boom meets a bill.
The policy danger is waiting until the bill arrives and then improvising. If utilities, regulators, data center developers, and communities do not build clearer rules now, every major project becomes a fight between national competitiveness and local consent.
That is a bad frame because both sides have a point. AI infrastructure may matter for economic and strategic reasons. Local residents are also right to ask why their grid, water, and rates should absorb private urgency.
So the story is not that AI is doomed by electricity. It is that electricity is becoming a gatekeeper. The next phase of AI will be shaped by model architecture, chip supply, safety rules, and product design. But it will also be shaped by substations, gas turbines, nuclear demos, fuel cells, transmission queues, cooling systems, and county meetings. The grid is the new GPU. For the Synthetic Lens, I'm David Carver.